Okay. Hello students, today we are going to be discuss about electric field and Gauss theorem. So, before going to discuss about electric field and Gauss theorem, just we will be looking to the about the electrons, protons and neutrons, how they are arranged in an atom. So, we know that in an atom centrally you will have protons, that is a positive charge you are going to be have, and around that electrons are going to be revolve. So, as we know that atom is in between the atom centrally center we have the positive charges, and around that we will be having the electrons we are having revolving, and these two are balanced the atom. And thereafter we have different scientists performed this experiments to know about the electricity, and then after we know that the electrical charge is quantized. So, all these things we know. Then after we will move into what is electric field, and we will see about the Gauss theorem. And now we will see about what is electric field. So, we know that electric field is nothing but it is in a region or a boundary, we can say that, in which we have a charged particle where the charged particle will be experiencing a force by other charged particles, and at the same time the other charged particles also experiences a force with this charge. So, this is known as electric field. So, we can say that an electric field is a region or a boundary around a charged particles where other charges experiences an electrostatic force. That is what the definition of this electric field we have. And if you coming to this electric field is an vector quantity. As we know that vector quantity is nothing but it will be having both magnitude and direction, both it is going to be have, and this electric field is represented by the electric field lines. Okay. So, as we discussed that electric field is a vector quantity which is having both magnitude and direction, and this electric field is represented by electric field lines, it is represented. And next, if you come to the properties of electric field, if you take, so the lines, that is nothing but the electric lines will be originating from the positive charges, and it terminates at the negative charges. That means the electric field lines will be starting from the positive charge, and they are ending at the negative charge. And we should know that another property of electric field, that electric lines if you take, so these are not intersect each other, that is they never intersect each other. So, they will have they will have the unique direction at every point. That means each electric line is having unit direction at every point you are going to be have. And if you take this electric lines of lines, if you take, as we have the more number of electric lines, that means the density of lines if you take, so that will be directly proportional to the electric field strength. That means, if you are having the more electric lines, then automatically the electric field is also going to be more. If you are having the electric lines are less, if you are having, then the electric field strength is also going to be less. So, we can say that the density of lines is directly proportional to the electric field strength. That is what some properties of the electric fields we have. Then we will be talking about intensity of electric field. As we know that electric lines will be there, so how much intense they are, that is what we will be calling it as the intensity of electric field we are going to be called. So, this generally this electric field intensity E we will be representing. So, if you take the electric field intensity at a point, it can be defined as the force experienced by a unit positive charge, otherwise a unit test charge. Okay. The electric field intensity is nothing but the force experienced by a unit positive test charge. So, here the positive unit positive test charge can be taken it as a q naught we can take. Then we can write this force experienced by unit positive charge as electric field intensity, that is E is equals to F by q naught we can write. So, the electric field intensity E is equals to F by q naught you are going to be have. So, if you take this intensity of electric field, it is also an vector quantity you are going to be have, and if you take the units of this intensity of electric field, if you take, so the units for this are Newton per coulomb you are going to be have, otherwise we can say that volt per meter also unit for this intensity of electric field you are going to be have. Next one, here we will be calculating this electric field due to a point charge, okay, electric field due to a point charge. So, if you are having a charge, due to that charge what electric field is there, that we are going to be calculate here. So, we know that from the Coulomb's law. So, what Coulomb's law tells is the force of attraction or repulsion between any two charges is directly proportional to the product of the charges. Suppose if you take here q and q naught are the two charges, q is the source charge we are going to be taken, and q naught is the test charge which we are going to be taken. Then the force which is present in between these two, the force between them may be attractive force or repulsive force, whatever we have, the force between them is directly proportional to the product of these two charges. So, we can write F is proportional to q and q naught, and at the same time the force between these two charges, either attractive or repulsive for whatever we are going to be have, the force between these two charges is directly proportional to the square of the distance present between these two charges. Suppose if q and q naught they are separated by certain distance r, then the force of attraction or repulsion between these two charges is directly proportional to 1 by r square you are going to be have. So, we can say that that is force of attraction or repulsion between the two charges is directly proportional to the product of these two charges, and at the same time the force of attraction or repulsion between these two charges is inversely proportional to r square you are going to be have. So, if you combine these force of attraction or repulsion between these two charges, then we can say that F is proportional to q naught by r square we can say. Then if you remove this proportionality constant, we can get this force will be equals to 1 by 4 pi epsilon naught q naught by r square you are going to be have here. And we know that the electric field intensity E can be defined as force by q naught, that is E is equals to F by q naught. Okay. So, then the electric field due to that point charge we can write it as E is equals to 1 by 4 pi epsilon naught q by r square. That means, in the force we know that 1 by 4 pi epsilon naught q naught by r square, and the electric field intensity due to a point charge we are calculating, that is given by E is equals to F by q naught. So, in place of F, if you substitute this 1 by 4 pi epsilon naught into q naught by r square, if you substitute, then we are going to get the electric field intensity due to a point charge, we are going to get it as 1 by 4 pi epsilon naught into q by r square you are going to be get here. Okay. And this in free space, or that is nothing but in air or vacuum, the value of this electric field intensity can be simplified, and it can get the value of like E is equals to 9 into 10 to the power of 9 q by r square, that is Newton per coulomb you are going to be get. That is the value of electric field intensity due to a point charge in free space you have. Right. Next, we will see about the Coulomb's theorem here. So, if you take a charged conductor, so this charged conductor has all its excess charges are distributed only at the surface. Okay. So, if you take any charged conductor, we can say that in the charged conductor all the excess charge whichever it is present, it is distributed only on the surface of the this charged conductor. That means, all the charges will be present on the surface of the charge you are going to be have, and the electric field inside of a conductor is 0 in in electrostatic equilibrium. That means, as we know that all the charges are present on the surface, inside of this conductor the electric field is 0 you are going to be have. Okay. So, the electric field just outside the surface is perpendicular to the surface and has a specific magnitude which is given by this Coulomb's theorem. Okay. So, what Coulomb's theorem is given is the electric field just outside the surface, the electric field just outside the surface is perpendicular to the surface and has a specific magnitude which is given by Coulomb's theorem here. So, if you want to state the Coulomb's theorem here, the electric field intensity E, if you calculate at a particular point, that is at the just outside of the surface, if you calculate. So, the electric field intensity E at a point outside of the surface of a charged conductor is directly proportional to the surface charge density sigma, and it is inverse and it can be given by E is equals to sigma by epsilon naught, it is given. So, that is what Coulomb's theorem we have. So, the Coulomb's theorem is nothing but the electric field intensity E at a point just outside the surface of a charged conductor is directly proportional to the surface charge density sigma, and its value is given by E is equals to sigma by epsilon naught. As we know that sigma is nothing but the surface charge density. So, we know that density is nothing but unit that is charge which is present in unit area. So, that units for that is coulombs per meter square. So, the charge is measured in coulombs and the area is measured in square meter. So, coulomb per meter square is the units for the surface charge density, and we know that epsilon naught is nothing but the permittivity of the free space. Okay, epsilon naught is the permittivity of the free space. So, overall the Coulomb's theorem can be measured as E is equals to sigma by epsilon naught we have. Right. So, now we will see about the electric lines of force. Okay, just we will see about the electric lines of force. So, the lines of force are electric lines of force, whichever we can call. So, these are nothing but the imaginary curves which are drawn in the electric field. Okay. So, the electric lines of force or electric field lines are nothing but the imaginary curves which are drawn in an electric field, So, if you take these electric lines of force, the tangent at any point gives the direction of that electric field E at that point. So, if you draw a tangent at any point, the direction of that electric field E at that point it is going to be get. Okay. And the density of lines indicates the magnitude of this field. So, if you are having the more denser lines of electric force, if you are having, we can say that the electric field is having the higher in magnitude you are going to be have, and we can say that stronger field means denser lines, we can say that. So, if you take the electric lines of force, these are the electric lines of force are imaginary curves which are drawn in the electric field such that the tangent at any point will be giving the direction of this electric field at that point it is going to be give, and the density of lines indicates the magnitude of the electric field. That means that if you are having the more number of lines, that is a more denser if you are having, then automatically stronger is the field you are going to be have. And coming to this property of this electric field lines. Okay. So, we will see the properties of the electric field lines we are going to be see. So, now first of all the property which we are going to be see is direction property, means how the direction of these electric lines of force will be there. Okay, how the direction of these electric lines of force will be there. So, if you take a positive charge, as we know that the charges you are having the positive and negative charges, if you take in the case of the positive charge, if you take, so these positive charges in this, the electric lines of force are radiated outward. So, that means these are going to be moved from positive charge away. So, from the positive charge they are going to be moved away, that is positive charge, why it is going to be move away means because the positive charge would be taken it as a repel, that is, since a positive test charge would repel, that is the reason why in the case of the positive charges these electric lines of force will be outward you are going to be have. And next, if you take in the case of the negative charges, so in the case of the negative charges, the electric field lines, these are converge inwards, these are converge inward. Because why these are going to be converged inwards? Because since a negative charge would attract, so that is the reason why the lines will be converging towards the otherwise inward of that charge you are going to be have. So, that is the property of direction. In the case of the positive charges, they will be radiated outward, and in the case of the negative charge, if you taken, these will be converge inwards. Why they are going to be converge inward? Because the negative charges will be taken it as a attractive we are going to be taken. Okay. So, that is one property, direction property we have. And next property of these electric lines of force, if you take, in the case of the electric lines of force, these electric lines of force never will interact each other. Okay, they never will be interact each other. If two lines crossed, the field would be two directions at one point you are going to be have, that is impossible. So, that is the reason why the electric lines of force, they never interact each other. That is one of the property of these electric lines of force we have. And next, if you go for this third property, these are perpendicular to the conducting surfaces. Okay, the electric lines of force are perpendicular to the conductor surface you are going to be have. So, at the surface, if you take, if you have a conductor, on the conductor, if you take the surface, at the surface of a charged conductor, the field lines, that is nothing but the electric field lines are normal to the surface you are going to be have. So, how the electric field line you are going to be have on a surface of a charged conductor is, they are perpendicular to the surface you are going to be have. So, since why? Because since charges move freely to cancel parallel fields. Okay, that is what we have. So, on a charged conductor, the electric field of lines of force are normal to the surface. That is one of the property you are going to be have. And next property, if you take the electric field of lines, so here in this case, again as we discussed, the density is directly proportional to the field strength you are going to be have. Another property is the density is directly proportional to the field strength we have. So, as we know that closer are the lines, that means more number of lines will be there. So, as density is higher, as we have the higher dense lines of force are there, then automatically the magnitude of this electric field will be more you are going to be have. We can say that it is a stronger field. That means closer are the lines, stronger is the field you are going to be have. So, example is for this one is near a point charge if you take. So, at that point charge you are going to be have what we call a more field strength you are going to be have. Okay, that is one of the example. And another property of electric field lines which we have is no closed loops in electrostatistics. There will be no closed loops in electrostatistics. That is, the field lines at positive charges and it ends at the negative charge. That means, the field lines will be starting from the positive charge, that will be starting point will be at the positive charge, and it is going to be at the ending at the negative charge. So, if you are having otherwise we can say that from infinite to negative charge it is going to be existed. That means, there will be no closed loops in electrostatistics. All the fields, electric field of lines, they will be moving from positive charge to negative charge you have, right. So, here we have shown some figure in which the lines of force are shown here. So, first one if you see this is the first one, at the center we have the positive charge we have. So, in this case the electric lines of force are radiated outwards. So, if you see the arrow mark is shown here. In this case, the positive charge electric lines of force will be moving away from the positive charge, which is we calling it as a radiated outwards. And next one, if you see, this is in the case of the negative charge, as we know that negative charge will attract all the electric lines of force, they will be converging to the negative charge. So, all the electric lines of force, if you see in this case, they will be converging towards the negative charge. So, whereas in the case of the positive charge, all the electric lines of force will be radiated radially outwards, they are moving. So, like this arrow mark is away from the positive charge, and in the case of this negative charge, all the electric lines of force will be towards the negative charge we have. So, this is in the case of the positive and negative charge. And here if you take the combination of the both the charges positive and negative, here if you take, so as we discussed that the electric lines of force will be traveling from the positive charge to the nearest negative charge whichever we have. So, in this case, if you see the electric lines of force, it is represented, they are started from positive charge and the arrow mark is represented here, they will be moving towards the negative point. That means, the starting point of the electric lines of force is at the positive charge we have, and they will be moving towards the negative point, that is end point is here, it is at a negative point you have. So, all these are shown with the arrow mark which we have. Okay. So, this is what the electric lines of force in case of the positive and negative charge which is present. And suppose if we are having two similar charges, here we have taken the example of two positive charges we have taken. As we know that in the case of the positive charges, all the electric lines of force will be radiated outwards. So, in this side they have radiated outside and there will be a repulsion between these two positive charges. So, that is the reason why in this direction they will be traveling, and the direction of these electric lines of force are shown here, which are moving from positive and radially outwards. This is what we have. So, this is the representation of the electric lines of force in different cases, in a case of a unit positive charge and in the case of the negative charge, and in all these what we call from positive to negative, and another case which we have is two similar charges. Okay. These are the lines of force which can be draw for different charges. Next one, we will be seeing about electric flux. Okay. Electric flux, what electric flux means. So, the electric flux, it can be represented with the letter phi E here. So, we can say that what actually electric flux means, the number of electric lines of force which are passing through a unit area is known as what electric flux we can say. So, here we can define this electric flux is nothing but it is a measure of the number of electric field lines which are passing through the given surface. Okay. So, if you have any surface, conducting surface or some other surface where the electric lines of force are traveling. So, how many electric lines of force, that is how many number of electric lines of force that traveling in that unit area, that unit area may be whatever it may be, the particular unit area they are traveling, that is what we will be calling it as a electric flux we are going to be called here. So, here if you take this electric flux, so we can say that it is a measure the quantity of flow of an electric field through a particular area. So, it is a measurement of the quantity of flow through a particular area in the electric field, that is what we can say that electric field. And if you take this electric field unit here, that is the SI unit of the electric flux, if you take, that is having the voltmeter, or we can represent Vm we have. Okay. So, which is equivalent to Newton meter square per coulomb, that is Newton meter square per coulomb, also we can say that that is the electric flux. Why? Because the number of electric lines of force, they will be traveling through a unit surface. Okay. Suppose if you take a uniform electric field and a non-uniform electric field. Uniform electric field is nothing but the electric field in which all the charges are distributed uniformly throughout the surface, that is what we will be calling it as a uniform distribution of this electric field we are going to be called. And if you take a non-uniform field, So, in which the electric charges are not distributed uniformly, whereas uneven distribution of the charges will be present, that surface we will be calling it as a non-uniform field we are going to be called here. So, if you calculate the electric flux in the case of this uniform electric field, suppose the uniform electric field, if I take E is the uniform electric field if I take, and the surface area of that uniform electric field is A if I have taken, then in that case, that is in the case of the uniform electric field, the electric flux phi E can be given as E dot A, and that can be given as E A cos theta. As it is a dot product, we are representing this with E A cos theta. That is, in the case of the uniform electric field, the electric flux is given by E A cos theta. And in the case of the non-uniform electric field, and as well as for the case of the curved surface, we can get the what we call electric flux as a surface integral of E dot dA. Okay, if you do the surface integral of E dot dA, you are going to be get this electric flux you are going to be get. That is about the electric flux. Now, next we will move to the what is electric displacement. Okay, electric displacement. So, if you take this electric displacement, it is a vector quantity. Okay, electric displacement is a vector quantity, and what actually electric displacement is nothing but this electric displacement describes how electric field will interact with the materials. Okay, how the electric field will interact with the materials which will gives us the electric displacement. Okay, and they separate the effect of the free and bound charges. So, this electric displacement separates the effect of the free and bound charges, it is going to be separate, and this electric field mathematically we can write it as a D is equals to epsilon naught E plus P we can write. Okay, this electric displacement vector D we can write it as a epsilon naught E plus P we can write here. Here we know that in this epsilon naught E plus P, epsilon naught is nothing but the vacuum permittivity we can say, and E is nothing but the electric field we have, and P is nothing but it is a polarization density. That is about the electric displacement. Next we will see about the Gauss theorem. Okay, here we will see about the Gauss theorem. So, here actually the Gauss theorem states that the total electric flux over a closed surface. Okay, here the Gauss theorem states that the total electric flux phi E over a closed surface, and this closed surface we will be calling it as a Gaussian surface we are going to be called, and this total electric flux through a closed over a closed surface is given by 1 by epsilon naught times the total charge which is present on the surface. Okay, what is the Gauss theorem states is, Gauss theorem states that the total electric flux phi E over a closed surface is equals to 1 by epsilon naught times the total charge which is present within the surface, or in that surface whatever may be the charge which is present. So, we can say that phi E is equals to 1 by epsilon naught times Q here. So, if you take Q is the charge if you have been taken, so we can write this as a Q by epsilon naught or 1 by epsilon naught times Q we can write here. So, phi E is equals to surface integral of E dot ds we can write, that is for any curved surface if we are having, then we can write phi E is equals to this surface integral of E dot ds we can write, and we can write this as a surface integral of E ds cos theta, which will be equals to Q by epsilon naught we have. Okay. So, here epsilon naught is the permittivity of the free space which we have. So, Gauss theorem as we discussed that it is the total electric flux over a closed surface area is equals to 1 by epsilon naught times Q you are going to be have. So, here in this case we have taken an arbitrary surface we have been taken, and in this we have taken a smaller area ds we have been taken. For that we will be calculating this flux, and then we will be applying for entire surface here. So, flux through that small area is given by d phi is equals to E ds cos theta we can give, and we will be taking the electric field due to a charge which we are going to be get it as a 1 by 4 pi epsilon naught q by r square, and we can get the d phi e value. D phi e is equals to, that is q by 4 pi epsilon naught d omega. Here d omega is nothing but the solid angle which is present. So, therefore, total flux we can give for an entire surface as phi e is equals to surface integral of d phi, which we can write it as q by 4 by epsilon naught surface integral of d omega. So, here d omega is nothing but solid angle. So, its value is equals to 4 pi you are going to be have. So, here if you substitute this surface integral of d omega is equals to 4 pi, we can get the total flux phi is equals to q by 4 pi epsilon naught times 4 pi. So, which we can get it as a q by epsilon naught, which is known as a Gauss theorem. So, if you are having instead of one charge, if you are having multiple charges if you are present on the surface, then we can say that phi e, that is total electric flux which is present over that surface will be equals to summation of the charge enclosed by epsilon naught. So, this is about the Gauss theorem which we have. So, Gauss theorem we have got the total flux which we have got is phi e is equals to q by epsilon naught we have got, and if we are having more number of charges on the surface, that means if you are having a multiple charges are present on inside of a surface if you are having, then by the superposition principle the total flux is the sum of each charge you are going to be have, that can be given as a phi e is equals to summation of q enclosed by epsilon naught. So, this is for multiple charges we can write phi e, that will total electric flux will be equals to summation of q enclosed by epsilon naught we have. So, this is for total multiple charges Gauss theorem can be tell.